Have you ever wondered what antimatter is and why it's one of the most intriguing subjects in the realm of quantum physics? Welcome to the world where the invisible becomes visible and the unthinkable becomes reality. This is the realm of antimatter. But what exactly is antimatter? It's a term you might have heard in a sci-fi movie or a Star Trek episode, but it's not just a figment of a scriptwriter's imagination. It's a real, albeit elusive, entity in our universe. Imagine everything in our universe, the stars, the planets, you, me, all made up of tiny particles. Now, picture a parallel universe where these particles have mirror images with opposite charges. This mirror universe is what we refer to as the world of antimatter. An electron has a negative charge, but its antimatter counterpart, the positron, carries a positive charge. Antimatter is a cornerstone in the field of quantum physics, and here's why. According to the Big Bang theory, the universe began with an equal amount of matter and antimatter. But here's the enigma. Where did all the antimatter go? Why is our universe dominated by matter and not antimatter? This is known as the baryon asymmetry problem, one of the biggest unsolved mysteries in physics. Now, you might be wondering if antimatter is so elusive. How do we even know it exists? Well, in the early 20th century, English physicist Paul Dirac predicted the existence of antimatter in his equations before it was ever detected. His work earned him a Nobel Prize and paved the way for a new era of quantum physics. So, we have a universe that should be teeming with antimatter, but isn't. We have equations that predict antimatter and proof of its existence, yet it remains one of the greatest conundrums in science. The enigma of antimatter continues to challenge and bewilder scientists and researchers around the globe. Stay tuned as we dive into the fascinating process of how scientists obtain antimatter. To understand how we obtain antimatter, we first need to understand its birth. Our story begins with the Big Bang, the cosmic explosion that gave birth to our universe. Around 13.8 billion years ago, an extraordinarily hot and dense point expanded, giving rise to space and time as we know it. In the immediate aftermath of the Big Bang, conditions were ripe for the creation of both matter and its elusive twin, antimatter. Antimatter is, in essence, the mirror image of matter. Every particle of matter has a corresponding antiparticle, identical in mass, but opposite in charge. When a particle and its antiparticle meet, they annihilate each other, releasing energy. This symmetry between matter and antimatter is a fundamental aspect of our universe. Given this symmetry, you might expect that the Big Bang created equal amounts of matter and antimatter. However, our universe is predominantly made up of matter. This discrepancy is known as the asymmetry problem. If matter and antimatter were created in equal amounts, they would have annihilated each other, leaving behind only energy. So, how come we exist? The answer may lie in a phenomenon known as CP violation. In the early universe, a slight imbalance might have tilted the scales in favor of matter. For every billion particles of antimatter, there might have been 1,000,000,001 particles of matter. The antimatter and most of the matter would have annihilated each other, leaving behind that one extra particle of matter for every billion. Over billions of years, those leftover particles of matter coalesced to form stars, galaxies, and everything we see around us today. This is just one theory, and scientists are still working to fully understand the birth and predominance of matter over antimatter. The asymmetry problem is one of the great unsolved mysteries of physics. Now that we know where antimatter comes from, how do we get our hands on some? Obtaining antimatter is no easy task. It requires precision, advanced technology, and a whole lot of patience. Now, you may wonder, how do we actually get our hands on this elusive substance? The answer lies in the heart of the most advanced scientific facilities on the planet. Particle accelerators. Particle accelerators, or atom smashers as they're affectionately known, are among the most sophisticated machines ever built. They propel particles at near light speeds and smash them together. creating a maelstrom of energy and matter. It is in this chaos that antimatter is born. When particles and their corresponding antiparticles collide, they annihilate each other, resulting in a burst of energy. But creating antimatter is just the beginning. The real challenge lies in containment. Antimatter doesn't play well with matter. In fact, they destroy each other on contact. So we need to keep our freshly minted antimatter away from any matter. Easier said than done. Scientists use magnetic fields to trap the antimatter particles. These magnetic traps prevent the antimatter from coming into contact with the walls of the containment vessel, which are, of course, made of matter. But even with these precautions, holding on to antimatter is like trying to hold onto a bar of soap in a waterfall. It's slippery and it doesn't stay put for long. To make things more challenging, antimatter is incredibly rare and fleeting. For all the energy and effort we put into creating it, we get very little in return. To put it into perspective, it would take billions of years to produce just 1 gram of antimatter using current technology. Despite these hurdles, the pursuit of antimatter is a testament to human ingenuity and perseverance. We're pushing the boundaries of what's possible, venturing into the unknown in the hopes of unlocking new secrets of the universe. But once we have antimatter, what do we do with it? That's the million-dollar question, and one we'll explore in the next scene. Stay tuned. Antimatter isn't just a fascinating scientific concept. It also has potential practical applications that could revolutionize our world. Let's delve into the boundless potential of this elusive substance. Imagine a world where we can harness antimatter for energy production. It could provide an almost limitless source of power. In theory, just a few grams of antimatter could fuel an entire city for a year. It's a mind-blowing concept, isn't it? The energy output from antimatter is about 1 billion times more efficient than burning coal, oil, or gas. But the potential uses of antimatter aren't limited to just energy production. Consider the medical field. Antimatter could be used in medical imaging and treatment. For instance, positron emission tomography, commonly known as PET scans, already utilize a form of antimatter, positrons. The potential for further advancements in this area is enormous. Now, let's take our minds off the Earth and venture into the cosmos. Antimatter could revolutionize space travel. With its high energy density, antimatter could be used to propel spacecraft at speeds we can only dream of today. This could open the universe to human exploration. The stars could become our new frontier. Despite the enormous potential, there are significant challenges to overcome. Currently, producing antimatter is incredibly expensive and time-consuming. Moreover, storing it safely is another hurdle, as any contact with regular matter leads to mutual annihilation, releasing vast amounts of energy. However, it's important to remember that all major scientific advancements come with their own set of challenges. The key is to continue exploring, experimenting, and learning. Because who knows, the next big breakthrough in antimatter research might be just around the corner. So, the question isn't just how do we get antimatter, but also what are we going to do with it once we have it? The future of antimatter is as mysterious as the substance itself. As we delve deeper into the fifth scene, let's take a moment to ponder the vast potential that this enigmatic material holds for our world. The key points we have discussed so far provide a glimpse into the mind-boggling possibilities. From the birth of antimatter in the high-energy aftermath of the Big Bang to the relentless hunt for these elusive particles, we've traced an incredible journey. We've also explored the potential uses of antimatter, touching upon its immense energy potential that could revolutionize fields from space travel to medicine. But where do we go from here? What does the future hold for antimatter? Ongoing research is pushing the boundaries of our understanding. Scientists across the globe are striving to answer intriguing questions about antimatter. Can we find a way to harness its energy efficiently and safely? Could antimatter be the key to propulsion systems that take us beyond our solar system? Or could it even unlock new treatments for diseases, using its unique properties to target and destroy harmful cells? these are not mere flights of fancy. Concrete steps are being taken towards these goals. For instance, researchers are developing techniques to trap and study antimatter particles, a crucial step towards harnessing their power. They're also investigating the fundamental properties of antimatter, exploring how it interacts with matter and light. This work could shed light on some of the deepest mysteries of physics, from the nature of dark matter to the origins of the universe itself. Yet it's important to remember that the path to these breakthroughs is fraught with challenges. Antimatter is volatile, difficult to contain, and the technology to manipulate it safely is still in its infancy. It demands our utmost caution, creativity, and above all, a spirit of scientific curiosity. So as we continue to unlock the secrets of the universe, who knows what new mysteries antimatter will reveal?